then I can look at for each n, then for each natural number here, you can look at the ball. It's always going to be centered at this x, but I'm looking at it with radii that is smaller and smaller. Right? If for each n natural number, if that ball was not contained in a complement, so this means that for each n you could pick, so pick xn in that set. So you just choose, right? Because we are assuming that the complement is not closed, it's not open. So it means that there would be exist at x, so that no ball here would be entirely in the complement. So this means that this one here would not be entirely contained in complement. So this means that there would be some xn, and this xn here would actually be in the set C, right? But now, of course, the distance here from xn to x, this distance here, is strictly less than 1 over n. So this means that, so this implies that the xn converts to x, right? And now the assumption was that whenever you have a sequence that was convergent, these guys lie in C, then the limit here also lie in C. So then you have, from the assumption that x here is in C, but this is the contradiction. You were assuming that x was not in C, right? Okay. And again, this here is really, really useful, but it's only useful kind of as a tool to proving things. It's not useful for checking whether an example is open or closed. Let me just quickly give you a couple of examples. Probably should have done that already. That if you're looking at, so what are closed subsets? Right, so closed subset could be, so here's some examples, closed subsets. So if it's an R, a closed subset is like some interval from, let's say, from 0 to 1, where both these points, both 0 and 1 is included. This here is closed. And why is it closed? Because the complement here is open. It's easy to see that the complement is open. Something like if you include one of the endpoint but not the other, this is neither closed nor open. Right, and also if you're looking at like the complement, say from 0, the complement of, so if you're looking at this thing here, union will say from 2 to 3, this is also closed. Okay, now maybe one more example is if you just take a single point. This here is closed. Right? And again, you just check that the complement is open. The next thing I think we talked very briefly about that last time, also because we talked a little bit about closed subset. But so if you you have the following theorem. So if you have a metric space here, and you have a family C alpha of closed subset, then the intersection of these closed subset this here, is also closed. And if you have just finitely many closed subset, then the union of finitely many closed subset is also closed. Right, and so here it's exactly the opposite thing as for open sets, that you can take any intersection and it's still closed. But if you take union, you can only do it for finitely many. So this is exactly the opposite. Why is it exactly the opposite? It's because that in order to prove that something is closed, it means that the complement is open. So, and then we have these basic relations for, right, so the proof of this again, so the proof of this, and so these were these operations on set that we went through, that if you take X here and you take the complement of intersections of subsets, right, this thing here is the same as the union of the complement, like that, right? And you see that since this is closed, this means that the complement is open, and you can take any union of open sets and it's still open. So that's why you could take any intersection, right? And so the other thing is that if you're looking at to prove that this thing here is closed, then you're looking at the complement of this union here. But this thing here is now the intersection, the complement of the intersection of the C1 up to, this is the complement of this is the intersection of these guys, like this. Right, and you see here, since C1 up to Cn, since they're closed, these guys here are open, and so you're looking at finite intersections of open sets, and that's open, right? So again, for closed sets, it's like in terms of taking intersection and union, it's exactly the opposite. Okay, now the next thing I want to talk about is a cover. So you have a metric space. So the situation is, so we have a metric space here, and we have a subset. A here is a subset of X. And then we have a collection, and then U alpha is a family of subsets of X, and we say that U alpha is a cover of A if A here is contained in the union of the U alphas. So this is what it means to cover that set by a family. A subcover of the cover U alpha is right? So if you imagine that you have like a whole bunch of sets, and together they cover A. A subcover means that you don't need to take all of the U alphas. If you can just take some of them, and they will still cover it. So a cover is a subfamily of the given family U alpha, such that the union of those still cover A. Okay. So let's look at a couple of examples. I mean, you know, if you take a family that covers something, then the family itself is a subcover, but that's a kind of trivial subcover. Right, and so you could look at, so just here as an example, suppose that the metric space is X with the usual, as R, sorry, with the usual metric. And suppose now that the U alpha is actually UNs, and those are intervals from minus N. Let me just make them open, it doesn't matter. You know, for a cover, there's no assertion whether they're open or closed or neither. So if you're looking at those sets, well, if you take the union of all of those sets, that gives you everything. So this family is a cover of the real line, right? Of course, if you take a proper subcover, right, meaning, right, I mean, you could take so this here cover all of it, but you see that this particular cover have the property that UN plus 1, right, this is contains the previous one, right? So you don't really need all of them to cover R. You could start, if you wanted to, you could start with at some very large N, and then you could go on from there, right? But you can't have, there wouldn't be finite many of the UN that would cover, right? You need infinite many to cover, right? Because otherwise, you know, there would be some sort of last point in both end. Okay, so that's a cover and a subcover, and an open cover. Open cover is then where each U alpha is an open subset. Right. It's not usually, I mean, it's really this that yeah. So that's an open cover. So each of the sets that is in the covering has to be open. And the last definition we need is a finite subcover. Is a cover, is a subcover consisting of finitely many sets. Right. Okay, so that's a finite subcover. And so now this leads to and again, you know, in this example here, on R, where this here is a cover, there is no finite subcover. So note that this this copper does not have a finite subcopper. Right? If you just take finitely many of these, they are not going to cover all of R. Right? But actually, in this example, you see also that the cover is an open cover. Right? Okay, so this now leads to the definition of compactness. So you have a metric space. So X, D is a metric space. A here is a subset. And we say that A is compact if for all copper, if for every copper for every open copper, so if for every open copper of A, there is a finite subcopper. Okay, that's fine. Now, and the thing that is really useful is, and we won't prove this today, but I'll prove it next time. So this is the following result. So why is this notion useful? Right. So one of the key property when you're thinking about sequences, one of the key property was for sequences on the line was the Cauchy convergence theorem. And the Cauchy convergence theorem again said that whenever you have a Cauchy sequence, then it was automatically convergent. And it was often much easier to check that a sequence was a Cauchy sequence than to actually find the limit and prove that it's converging to that. But to prove the Cauchy convergence theorem, we needed the Bolzano-Weierstrass theorem, right? And so this is because, so why is it useful, this notion of compactness? So it's useful because there's a metric version of the Bolzano-Weierstrass theorem for metric spaces. And so this is the following theorem. And again, I won't prove it now, but I'll prove it next time. That if you take a metric space and A here is A is a subset and A is compact, then any sequence in A has a convergent subsequence. That's right. And so remember that the Bolzano-Weierstrass theorem again said that if you take a bounded sequence, in R, then there is a subsequence that converge. Okay, so now let's prove a few things about right. Let me also look at a couple of more examples. So the first thing I want to just discuss is that, so this here is like the key, this is our key application of compactness, that you have this metric version of the Bolzano-Weierstrass theorem. And so, and now, but let's prove a couple of things about compact subsets. So we have a metric space here, and I have A here is compact. Then I want to show that this implies two things. One is that A is bounded. And the second one is that A is closed. Okay. Let's prove first that A is bounded. Well, you could, yeah, no. You could look at, so you could look at a very trivial cover of A. So, so you have here A. Well, obviously, if you take all balls, let's say with radius 1, and you take all balls, but now the center here could be anything in A, right? For each element in A, you take a ball of radius 1 around that point. But that's, first of all, these balls are all open. And of course, this thing here, the union of these guys, well, a union contained in particular all the centers, but the centers is already A. So you trivially have this, right? Now, since A is compact, this means that A must be that this is an open cover, so this means that finitely many of them already cover A. So you have finitely many. Like this, okay? But now I claim that this automatically implies that A is bounded, because you see, you have all these balls here. And A is somehow contained in the union of these guys, right? So this means that for any element, so this means that for any X, so if X here is in A, then there exists one of these finitely many I, where I is one of these finitely many, so that the distance to this xi is smaller than 1, right? We would like to say that A is contained in a large ball, right? So now, and that, right, so now, now you just take the, you pick one of these xi's. Let's pick the first one. And let's look at the maximum of these from the first one to the other one. And let's add 1 to that. Right? That you take a maximum over finite many numbers. So this is a nice finite many numbers. And this here is, you call this here R. Now you look at the ball of radius R around x1. And I want to show that any x, so want to show that for any x in A, then we have that x is in this ball, like that. Okay. So, right, so now we know that, so since x here is, we know that x is contained in the union of these balls. So we know that x is contained in this ball here for some I. Where it's one of these little n many i's. Right? So this means now that the distance, and so you know that the distance to this little I is at most 1, right? And so now if you're looking at the distance from x to the first one, then this here is less than the distance from this to xi plus the distance, this is the triangle inequality again, xi, maybe let me just make very clear that this is the first one to the first one, right? This is the triangle inequality, right? But these distances here are, right, this here plus this is, right, so this here is, so, sorry, this thing here is bounded by 1, right? It's actually strictly less than 1. So this here is less than 1 plus this thing here. And you see this thing here is, of course, this is how we define R. This is strictly, this is actually less or equal to R, right? And so you have that this thing here is strictly less than R, and that's what we want to prove. Okay, so this proves that if you take, again, a metric space and you have a compact subset, then it's automatically bounded. What about the second one? Suppose you take a subset, is it closed? Now let's use the theorem that we just proved. So we need to prove okay, so let's prove that this A here is closed. Okay, so now if A is closed, so to prove that A is closed, by the theorem we proved just a little while ago, theorem we proved earlier, we showed earlier, we need to show that if xn is a sequence in A, and xn is converging to some x, we need to show that x is also in A, right? Suppose not. Suppose not, we want to show that this leads to a contradiction. We want to get a contradiction. So you have this x here, and you're assuming that the x is not in A, but yet you have a sequence in A that somehow tend to this. This is the sequence xn, and it's tending to this element. Well, we saw earlier that we defined something called E here, which is the x, the y in x, so that the distance from x to y is strictly bigger than r. Then we saw that this here is an open set, right? We show that this here is open. This is for each r. So I'm going to now find a cover of A. I'm going to find an open cover. And the open cover is that for each integer, for each n here, I'm going to look at E 1 over n. So this means that I'm looking at the y, so that the distance from y to this x here that I want to show is in A, that this thing here is bigger than 1 over n, right? But now I claim that A here is contained in the union of these guys, right? Because you see, these guys, actually, these guys here, if you have something that is not in any of these, right? This means that this inequality fails with each n. But this means that, so if x here, if z is in the complement of the union of these guys, then actually, then you have that this thing here is less or equal to 1 over n for all n. Right? You have that, that's a complement, right, of the union. But if it's less than 1 over n for all n, it means that it must be 0, right? So it must be, so it means that this distance here, so you conclude that this distance is 0. But this means that this set here is actually your x, right? So the complement of these guys, the complement of this union here is simply just the point x. But you are assuming that x was not in your set A, right? The complement here, the union of these guys, we have proved now that the union cover everything but x. So in particular, it covers A, because we're assuming that little x was not in A, right? Okay, so this is a nice open cover of A, but A was supposed to be compact. That means that finitely many of these cover, right? But now this family has this property. Family has this property that you see these guys here, if you're looking at E 1 over n, this thing here is contained in E 1 over n plus 1, right? If this number here is smaller, then it means that this set here is larger, right? So you have this, and so you see that if finitely many, if A here was contained in finitely many of these guys here, if it was containing a union of finitely many, then you just take the one of these ni's that is the largest, right? So this means that A here would be contained in some 1 over of some for some I, right? Because there's one of these numbers, these ni's, that would be the largest, right? But this means now that A, right, that there is some lower bound for the distance to x in A, right? It doesn't, there's no elements that is, so this means that there does not exist, let me say it, for all y in A, then the distance here from y to x is strictly bigger than 1 over this ni, right? This is just some fixed number, right? This is obviously, right? But this means that you can't have a sequence in A that is converging to x, right? Right? Because they all stay away from x, right? They stay a certain positive distance away from x. So this means that, so this is the desired contradiction. Therefore, there is no sequence xn that converts to x and the xn on A. But that's what we assumed in the beginning, right? We assumed, we wanted to check that whenever you have a sequence in AN that is converging, then the limit was also, right? So there was supposed to have been such a sequence. So that's a desired contradiction. So this proved that if you take a compact metric space, then if you take a metric space and if you take a compact subset, the compact subset could of course be all of x. That's fine. But if you take, but I want to allow more generally that just to say that just having a subset that is compact, this means that it's bounded and closed. If you are in Rn, so you have a theorem, and we'll talk about that next time also, that there's a theorem that says the converse is the case. But that is not actually, that does not generalize to metric spaces. So there's a theorem here. Well, I mean, it does generalize, but not like this. It's not, that this particular statement does not hold. So in Rn, with the usual metric, say the usual Euclidean metric, if you will, you can just think about R. If A here is closed and bounded, then A is compact. Okay. I wanted to talk about an example, but I don't think I have enough time to actually talk about that. Let's talk about this, return to this next time, because we only have 4 minutes left. And so instead, let's prove a theorem here that if we take the theorem, if you have a metric space, A here is a subset of X, is compact. Suppose that C here is a subset of A, and C here is, right, so this is of course in X, so C is also a subset of X, and C is closed, then the claim is that then C is also compact. Right, and we have 3 minutes, and we don't need 3 minutes because it's actually very quick. And so the thing is, so proof of this, so C here is assumed to be closed. So this means that since C is closed, this means that the complement of C is open. Right? So now let O alpha be a cover of C. Then we can, so O alpha is a cover of C, and now you can add the complement of C to it. So if you're looking at C, so C here is now, of course, you see here, so in fact, A here, you can think about A as, so A is clearly contained in C union with the complement of C. And so this means that A here, the O alpha cover C, so this is contained in the union of O alpha union with this last set, right? These guys are assumed to be open. This here is open because C is closed. So this means that you have now A is contained in, this is an open cover of A. So this means that finitely many of these, right? So this means that A is contained in like O1 union up to some ON, and then quite possibly you would also need this one here. But now you see, but C here is contained in here. So this means that C is contained in this. This here was not part of the cover, but it's not needed if you just want to cover C, because none of these elements cover anything in C, right? So this implies that C actually must be contained in O1 union up to ON, because this here does not cover anything in C. So this proved, right, that C, there was a finite subcover that covered